so this is a little bit about the history of how we know. We kind of cheated and said that we have infrared cameras and X-ray detectors and things like that, so we just peer through the dust. But the historical argument is pretty interesting, and again, really important technique. So you're told to remember these funny stars who aren't sure if their cores are puffy or not puffy, and now this is when we use them. Okay. So again, the argument is you see this, and then we're not going to get any appreciably closer or farther from this. There's no way that you're ever going to change the view. And then we argue that we're in, the suburbs of a spiral galaxy. We know it's got more of a bar-like structure. These things all have names. We're in the Scutum interarm spur or something like that, and there's the Orion arm and what have you. So it's a pretty precise claim. And we started here is people didn't even think the Milky Way was stars. In fact, galaxy, the root word galactos, lactose, still, like somebody spilled milk in the sky. Till Galileo was able to resolve the fact that the star was, made of innumerable stars, and the Milky Way itself was granular. So he was maybe the first astrophysical measurement of the Milky Way is like, holy crap, it's a lot of stars. It's so many stars that we can't even resolve them. This was done back in 1610 with the aid of, maybe like 30 times magnifying glass. And then nothing that much changed. The big technological innovation to this point was that if anybody's ever taken an optics class, you know that lenses are pretty bad, and they have all sorts of things like spherical and chromatic aberration, and to make a perfect lens that faithfully sends to you the light from an astrophysical, light-year distant object is pretty difficult to do. And it might even prism the light out and smear it. So Newton actually solved this among his many other achievements. He came up with the idea of a reflecting telescope instead of a refracting telescope. So instead of a big lens there and there, there's light that comes in, it collects in a big bowl-shaped mirror. Parabola would be amazing, but you can get by with a sphere. And then it gets focused somewhere else, and then you stand on some observing platform. So this is a human in this scale. This is not Newton's day. This is like 1770s, 1780s. And then you collect that light and then observe it. So you don't have a really important next technological innovation, but people had figured out how to engineer like 40-inch mirrors at this point. And you have all these mechanical cranks, move them around. I think it was fixed, but in an older edition of one of the textbooks that's been used, this guy, William Herschel, is born in like continental Europe, and somehow, I don't know how you get this job, but he was, it's like playing the glockenspiel or the piccolo or something like that in a military band, and saw his first taste of combat while playing the piccolo, and he was just like, screw this, I'm going to England, and turned into an amazing astronomer. Sometimes Caroline Herschel, at least in one book, is quoted as his wife. That's messed up. That's his sister. They were this amazing duo where they would make their own telescopes. They would like pour lead to make their own perfectly spherical mirrors and then silver them themselves. And this is all homemade. It's really impressive. And they were basically the premier astronomers of the late 18th century. And they tried to do something which there's a lesson about how even very smart and dedicated people can fall into this very seductive thinking, is they surveyed the heavens. So they did this in the way that you might be like, I don't know, a forest ranger, and you work in a national park, and you go out to like plot A, and then you count the number of ferns or the number of like skunks or something like that, and then plot B, C, D, and then you use your counts to basically make like a map of how frequently you see these ferns or this wildlife. So they just pointed their telescope in like random directions that they could get to, and they counted how many stars they saw within that field of view. And they made a census of the entire universe. And this is the Herschel census of the entire universe. And this is the sun, our solar system. Any guesses about what this weird kind of gappy feature is, actually? Zoom back a little bit. So you see a big overdensity and then an underdensity. And remember, these guys, yeah, they don't have parallax, so that's exactly right. This is a dust plane. And in fact, the center of the galaxy is out this way. And what they were doing is they were just presuming that stars were evenly spaced. And so if they saw, like 50 within their field of view, they would evenly space them along that lens. Does this agree with your sense of what the universe looks like? No, I don't think so. What was the thing that they didn't understand, which is the bane of astronomers to this day, honestly? It's a 4-letter word in the astronomy community. And for everybody else, actually. Dust. So this is kind of the fallacy that they fell into, is that you just like knocked yourself out. You completely forget who you are, what it's like to be a human, what planet Earth is, total memory wipe, and you wake up in the middle of the woods. And this is the first kind of scene that you see. And as you look around, you say, this is kind of interesting. So I'm going to, I see some trees this way and this way and this way, and I presume that the universe is, this big around. It goes until that tree. That's the last tree at the edge of the universe. Because the dust extinction was so great that they just kind of stopped seeing stars, and they presumed that was the edge of it. There were no more stars. What they didn't realize is that, of course, there's more stars, and what we haven't even talked about, even though we now know that there are other galaxies out there. In 1780, there was not an idea that we are one galaxy and there are many others. So this is kind of like the analogy of what they were thinking, because they knew no better, and we're not going to get off of this planet. So to put that kind of in perspective, this is the Herschel Map. So it should be even a little bit smaller than this, but about so that's about how deep they saw. And this is cutting edge, and they weren't want for mirror size, so it had nothing to do with the optics. So parallel to that discussion, and somebody who's famous for another reason, Immanuel Kant, actually weighed in on this. I don't know why. He's just really interested in galaxies. Is that the people who did the extra credit now know about this Messier catalog, right? And these are the Messier objects from 1 to 110. And they kind of come in 2 flavors. So there are things that look like this, that, and maybe even that. And then there are things that look like this. So this is M31 and that. And we know the answer, but we're spoiled. Back in the 1780s and 1790s, this was actually kind of a puzzle, is what are these so-called spiral nebulae? So are these just kind of whirlpools of gas? Is this a really young star that's starting to form? Is that what's going on? People actually thought these so-called planetary nebula, they were forming a planet in the center, all the stuff was coming in. It's a terribly bad idea. Is this going to be a star at some point in the future? What is it that you need to know to resolve this? So to make the claim that, this, what we now know as the Andromeda Galaxy, is actually really a totally separate city of, 200 million stars. What is the thing that you need to know? What would you do if you had the amount of light coming in? So by amount of light, do you mean an apparent brightness, or do you mean absolute brightness? So maybe, but they didn't know the answer because they didn't have this piece of information. So, maybe we could phrase it like this, is there's about as much light coming from this as something like that. Actually, Andromeda is really bright, so why don't we do this? There's about as much light coming from this, which is a globular cluster in our own galaxy, as there is from that, which is a distant galaxy. So the apparent brightness is similar. How do I know one's totally separate galaxy and this one's just a blob of stars that's relatively close by? The extra thing I need is what? There are actually 2 answers. Possible answers. Yeah, I either need to know the distance, that's what I want to get at, but the other way of asking the question is, how much light is this actually putting out versus that? Because if this is, like 10 billion times more light, actual luminosity than that little cluster, if I could somehow find that out, I would know. And that's hard. It's actually pretty difficult. Not in 1780, it wasn't gravitational lensing. So we need to find some kind of steampunk techniques to do this, to do the historical argument. And the answer turns out to be some special stars. So certain types of stars will tell you something about their intrinsic luminosity. Because even if you see a big blue star, do you know if it's an O star or a supergiant? I don't know. Especially red stars, they're so treacherous. It could be an M or it could be a giant. It could be 8 orders of magnitude difference. So, yeah, very slippery. Even more so because, even until 1880, 1890, probably happened pretty quickly, so maybe 1870 or 60, is that this is how people are working. So what other really, really, really important technological innovation is missing from this? So this is William Parsons, another famous astronomer from dismal, cloudy Northern Ireland, I think. He was in Ireland. I don't know, terrible place to do astronomy. But this is what he was presenting, right? So he'd look through his eyepiece and he would sketch in charcoal. And we still do this technique where this is like what we would call a negative image, where the shaded part means more light is coming from that. So this would be a bright central bulge, and then these would be bright bands with a bunch of stars and spiral arms. So what are we waiting for before we can actually do some like meaningful precision astronomy? And something else that's very miraculous. So the human eye only collects light for like 1/10 of a second before it refreshes its neurons, whereas a photograph could just sit and collect it indefinitely. So this is actually a really difficult business. These like the spiral nebula problem. And people, it's basically like the argument of the day. Is these swirly clouds of gas, are they separate galaxies, like separate from our own, really far away? They would call them different universes. Kant called them different universes. Or are these just swirly clouds of gas in our own galaxy? And they fit within the little Herschel picture. So just to compare, this is what we're able to do with like Hubble Space Telescope, and this is what Parsons was doing by hand and sketch. I don't know if it's that good, but that's what they had. It's really valiant effort. Okay. So nebula if it's cloud within our own galaxy, and galaxy if it's outside of our own. So what's that, nebula or galaxy? I'm not keeping poker face. We'll go with first answer. What's that, nebula or galaxy? I'm trying to pick the hardest ones too, just so you appreciate the difficulty of this. Split, nebula, galaxy. Nebula or galaxy? Nebula or galaxy? Okay, so it's hard. We forgive them. They had no photographs. For some reason, they were observing from Northern Ireland, which is like a miserable, damp, rainy place. Okay, so nebula, galaxy, nebula, galaxy. And I picked the weird-looking galaxies, the so-called irregulars. So it's hard. It's a difficult problem. And what we really need to do is we need to find distance. So the unambiguous answer comes from, I need distance. And so far we have distance through parallax. Parallax would get you like halfway through that little Herschel diagram. So parallax works to, like a couple hundred light years. The closest major galaxy, Andromeda, is 2.5 million light years away from us, so parallax is not going to cut it. And it turns out the answer comes from these things, is that we mentioned that when you're talking about stellar structures, that these actually, because their mass to luminosity ratio is pretty high, they have pretty dense cores, and these, because their mass to luminosity ratio is pretty low, they have really puffy cores. And there's a little bit of a kind of turnover point there. And secondly, as they age, what happens is these kind of white stars in the middle on the so-called instability strip, they start making heavy elements. And they actually form like kind of like a creme brulee kind of crust on top of their core. And the radiation pressure from the core actually kind of builds up beyond this crust, and every once in a while it'll puff the crust out and it'll be brighter, and then the crust will contract. And they actually beat like drums. So they'll get much more luminous and then less luminous and more luminous and less luminous. This is a huge one. This is a variable star, and this is its brightness. This is in magnitude. So this is going from 5th to 14th magnitude. It's pretty nuts. So this is a wild change in brightness. And this happens over the course of 1997, 98, 99, 2000. So over the course of a year, basically, this star will increase and decrease in brightness by a tremendous amount. So what? Well, actually, first let's do this. So here's a globular cluster, which is where you tend to find them because they're older stars. Do you guys see the variable star? you think I'm missing it now? There. See it? Maybe you have to be in like the front row. Right there. What you really need is a couple of photographs, right? Like to look at that and then come back a year later and say like, oh no, that star was much dimmer when I looked like last June or something. So it's not necessarily, so you fake the time-lapse thing with, they used to have these things called bladed interferometers where you just like switch back and forth in between two photographs, stills, like it's like camera 1, camera 2, camera 1, camera 2, and then your brain processes it. It's basically like an analog version of a GIF. But what you really need is a photograph, because to sketch this and say like, well, there was a really bright star there, I'm sure of it, would be really difficult. So people could have done this before photography, but not really. And that's the next major innovation in astronomy, honestly. Like you can have this thing collect light for a very long time. In some respects, photographic plates don't exactly pick up the same wavelengths that the human eye does. So you kind of can escape, just visible light. But there it is. There's a variable star in a globular cluster. And no, it's and it's hard to find there are a couple weird ones, but it's this is like a typical variable star. It's in the right place. It fluctuates a little bit. There might even be a second one in here, I think. I don't remember. Maybe there's another one there.
So take a really good.
What's that? Do you see it? Blink in and out? Yeah. So there now it's there. Now it's gone.
Oh, it is actually.
Now it's it. Yeah.
Okay, I didn't.
This is subtle, right? No, it's totally animated. Right? I was just messing with you guys. So next time I'm just going to bring in a static image and just be like, you don't see it? I think I've lost my mind. No, so that's a variable star. Okay. But this is the important thing, is imagine that you just hear like, I don't know, you're traveling in some really far off land and then you hear the people who live there playing these weird musical instruments, and one plays this very, very, very low bass note and another one plays a very, very high-pitched treble note. What do you think is true about the size of the instruments? So the bass probably comes from what? Just based on your own experiences from going to the orchestra or something like that. Big thing. And then Herschel would have known this because he played the piccolo, or maybe it was a clarinet, I forget. But the faster pitch, the higher frequency things will be smaller. And somebody took this idea, one of the Harvard computers, Henrietta Swan Leavitt, and she said that, maybe it's true that the little things pulsate faster and big things. And by big, she really meant luminous and not luminous, because that's the important question to ask. And she painstakingly went through and did a survey of a particular type of variable stars. Unfortunately, they come in a couple of different flavors. But for hers, the so-called Cepheid variables. And you can see them out into our little satellite galaxies, the Magellanic Clouds. And what she discovered is that their average luminosity, granted they change, so their average luminosity, which in units of the sun's luminosity, these things are really bright. They're in between, 1,000 to 30,000, those are logarithmic units, 1,000 to 30,000 times the sun's brightness, or can be. And they vary on human-accessible timescales, too. So the dim ones, turns out she was right, and they pulsate faster, the little ones, little meaning less luminous. And the ones that pulsate more slowly are much more luminous, so these kind of giants heaving in and out. And so this period luminosity relationship actually lets you do something really important. This is how we worked the first time, is when we actually resolved this problem of how bright is a star, like actually for real, what's its power, we needed to know distance. So we took the distance, which we got through parallax first time around, and the apparent brightness, how bright it appears on Earth, and we corrected for it and we found the absolute brightness. So now we have a sneaky way of doing this, in a sense, in reverse, is if I told you that I saw a so-called Cepheid variable and it had a period, it pulsated once every 20 days. What could you tell me about it? So I see this thing vary in brightness once every 20 days. Well, this is logarithmic, so we shouldn't take it too seriously. So 20 days is probably around there-ish. Yeah, 3,000-ish times the sun's luminosity. But the important part is that that's luminosity. That's not apparent brightness. The apparent brightness has to do with something else. That's how much power it's actually putting out. So I actually have a way of taking the observed period, which tells me the luminosity, and the apparent brightness. And what's the thing that turns my apparent brightness into a luminosity? The missing piece is what? Distance. So in fact, by observing how fast this thing is wiggling and how bright it appears, you can actually find the distance. And this is good because you have these distance markers that can be up to 30,000 times the brightness of the sun. And she was able to see them in the Magellanic Clouds, for one thing. And the Magellanic Clouds are outside of our own galaxy. So there it was. And this will be part of something that we call the distance ladder. So what she needed to do this, establish this calibration, was she needed to find their distances and find their actual luminosities. So she needed to find ones which had been measured by parallax or something else similar to parallax. And so there's this thing that astronomers call the distance ladder, where each way to establish distance, you like hand over hand and pull yourself farther into the cosmos. And the variable stars are a really, really good one because they were the ones that let us get out of the galaxy. Okay, so here's like the Herschel map, and this is our sun, and this... Did you feel at home with that picture? I mean, you kind of know where we actually are in the cosmos. But we were sitting dead smack in the center of the universe in the Herschel's world. And kind of revived this like Copernican idea, right? They put the solar system at the center of the universe and said, look, we see equal numbers of stars on all sides. We're like at the center. And now people actually have enshrined the advice to not do that as something called the principle of mediocrity. It's really like, no matter what you do, the Earth isn't special and you're not special. Just really like kind of disheartening, but it works really well. So it turns out that if you take measurements of variable stars, which you see in globular clusters, like the animated one, and the person to do this was an American astronomer named Harlow Shapley, and he basically, so here's the dust plane. This is the terrible place where you can't really see stars, and you can see there's like a real underabundance of data there. Is he looked at the globular clusters that appear in the halo above and below, and he was able to see individual variable stars on them, and he used Henrietta Swan-Leavitt's luminosity period relationship to figure out how far they were away. And he made this map, and he said, holy crap, they're really far away. And there's this kind of central lump, so this is almost the central feature of where we're in. And the total distance he got was about 300,000 light years, about a factor of 3 too big. What was it that Shapley didn't understand and made things look dimmer than they actually were? It could have been an issue, like a systematic issue with the stars themselves, but there's a easier answer, which is the bane of all astronomers everywhere, is that what could make something look dimmer than it actually was? Dust, right? So we've changed this a little bit, but dust. Okay, so Shapley continued to reason that maybe he wasn't seeing the stuff on the other side, and to live inside of a coffee cup-shaped universe would be a little bit weird. So it should be symmetric due to gravity, and he was able to make a picture that looked like this. That, like, even with good telescopes, you're only going to resolve individual stars at about this size. So this is Shapley's picture, and he went on to argue that this was the shape of the galaxy. Everybody agreed with him. This is still an unresolved question about what these things are. In fact, that guy Shapley didn't believe that these were other galaxies, like separated far outside of our own, even though the variable stars were the tool to figure out whether or not they were. So what do you need to do if you want to use variable stars to establish the distance to this? You'd actually have to see one. So you'd have to resolve a single star within a galaxy, which almost seems hopeless. And so even the person who used this technique really successfully to map our own galaxy just didn't quite understand or didn't have the data to solve this spiral nebula debate. Fast forward a little bit, and this is the first time we run into this character, is somebody named Edwin Hubble, who's kind of famous, was using the 100-inch Mount Wilson Observatory telescope. So this is, I don't know, 100 inches is like mirrors about this size. I actually got to observe a night on something that was like 2-meter class. And when you move it around, it's like driving a school bus. It's actually kind of scary. So the thing like slews. Just like, man, if I press the wrong button because it's mechanized, it could just like smash in through the floor or something like that. But it's really an incredible instrument. And he was able to observe M31, the Andromeda Galaxy. And it actually, lore is he found it, but in actual truth, Mount Wilson's outside of Los Angeles, back when Los Angeles did not have so much light noise that you couldn't do this, and no infrastructure. So they got supplies to the observatory by somebody who just like brought up a pack mule with stuff. And the deaf high school dropout who brought up the supplies and the mule was like, hey, can I try the telescope? And it's like, sure. It turns out he's like a really good observer. So the actual photographic plates, you have to sit there and you adjust for the atmosphere manually. So you're just like knob twiddling to keep the thing in perfect focus. And this guy actually took most of Hubble's plates, but Hubble is famous for it. He wrote the paper, and he knew what they meant. But long story long, in here, so this is the Andromeda Galaxy. You zoom in there, and you zoom in there, and this is Hubble's original plate. So right there in these bars, you can see he's really excited about it. Bar! Exclamation point. Out in a globular cluster in Andromeda's halo, he found a variable star. And he found the variable star, he observed it, he was able to find its period. If he found its period, then he was able to find its luminosity and therefore brightness. And luminosity and therefore distance. And this distance put the Andromeda Galaxy squarely outside of our own Milky Way galaxy. So this would be his number. Again, not great, was just under 1 million light years. Modern estimates are 2.5 million light years. Same culprit. These things weren't calibrated as well as we have them done now. It's dust. It's always dust. But this is it. So this is actually, it's also a GIF. And you can see this going by like 2 weeks. So this is HV1, which is kind of a famous name, Hubble Variable 1. So you're getting brighter and dimmer and brighter and dimmer. And that's with Hubble Space Telescope. So it's kind of an homage, I guess. No, the subtle changes that you see there are other annoying effects, like whether or not things get cut off in pixels. This is a space telescope, so it doesn't have to worry about the atmosphere or anything like that. So the mild variations you see are things like normalizing the camera and technological things. It's not, it's not overexposing the frame or anything like that. Yeah, it's kind of weird. You take the same picture with the exact same CCD camera twice, and you might get like slightly different pixel counts and things like that. Say again? So this one is the variable star. So it's increasing and decreasing in brightness. And the rest are just, I don't know if they're main sequence or not, but they're not variable stars. So it's just the one in the center of the frame is very, very bright and pulsates. Basically, every couple of, I guess it's every 2 months or so, maybe 4 months, which would be at the higher end of the Cepheid variables. So this would be like 10,000 times the luminosity of the sun, maybe. Okay. So 2 things happened there. One is we got to laugh about the Herschels. They wore powdered wigs, and they thought we were at the center of the universe. It's wrong. And then secondly, this idea of variable stars is important, and their existence is a rung on the distance ladder. So we'll talk about a couple more, but right now we have 2 rungs on the distance ladders. We have parallax, gets you out to a couple hundred light years, and then variable stars. All of a sudden we're outside of our galaxy. And then Hubble will come back and talk about standard rulers and redshift, and that will get us to Hubble's law, which is the next piece, which will happen early next week. Any questions about that stuff? Okay. It's your turn to do this. And